Hello? Is this working? Is this working now? Yeah? Okay. Hello and welcome to the talk Neural Networks by Example. My name is Katya Mustafina.
And my name is Natalia An.
And we'll walk you through this talk about neural networks fundamentals. Is anyone doing machine learning in here? Anyone doing deep learning?
100%.
Yeah.
100% of people doing machine learning, doing deep learning. That's awesome.
So this talk is about neural network fundamentals. And neural network is an algorithm. That's a computational method. And that's a machine learning paradigm. But before we start talking about machine learning, I wanted to talk a little bit about before we start talking about neural networks, I wanted to talk a little bit about what is machine learning at all. And okay, so here is a traditional computer program which is very good at detailed instructions such as assignment operations, loops, or conditional statements. And what it does actually is that in some computer language, it's implement an algorithm that is converting some input to some output. So we instruct the computer to take our input and produce the output with that. So if we look at the computer program as an abstraction, for example, we can think of it as a function. A function is some computer language that takes an input and produces an output. So at this point, I wanted to restrict myself by pure numeric functions and computational functions. That could be, for example, linear functions or any function that, for example, the one complex one presented on this picture, or it could be quadratic function or something. This restriction is I'm doing for better intuition about machine learning because actually machine learning is dealing with numeric calculations. So now to intuition about machine learning. So imagine we don't have our function, but what we do have, we have a set of data, some inputs and some outputs. But we don't know how it has been calculated. We know that this input produces that output, but we don't know how. We don't know the algorithm. But what we do, we take a pool of functions, maybe infinite variety of functions. Each of those can be a candidate for that calculation. And then by doing experimentation, we are choosing the one that fits best to our data that we know to be correct. And then we choose it for calculation of data of similar nature. That process is called training. And the data that we use for training, the data that we know to be correct, is called training data. So that is very roughly intuition without machine learning and what's actually happening. So what is neural network? Neural network is exactly our function. And this is an algorithm implementing very complex nonlinear functions. And that is a feature of that algorithm. And that will go into detail later on in the talk. But before we do that, what I wanted to talk about that is that why do we care at all? Why neural networks becoming so popular or deep learning is becoming so popular these days? What kind of problems deep learning can solve that couldn't be solved before and then now can only be solved by deep learning in neural networks powered engines. And the first interesting application is computer vision. A computer can recognize objects. The face recognition is something that we are using every day on our mobile phone. If you have your Apple photo library or Google photo library, if you are doing auto-tagging in Facebook, that is the face recognition. Handwritten text recognition. This is very classical application that will go deeper later on in the talk. Also, online search. Google is using neural networks to classify its images. And then by entering the word giraffe, you can see lots of images of the giraffe. Also, if you don't know some word in foreign language, in Chinese, for example, you can enter it, and then you can see the pictures. And you can very likely to see the pictures of that object. You can search your image, and you can search similar images on the web. That is powered by neural networks. In security, a computer system can recognize the person entering some premises. We are using our fingerprint recognition to unlock our phones. And you can use, for example, a computer system to survey the public places like airports to detect people who are actually behaving strange and they are not, they can be potentially dangerous for someone. They maybe have a bomb with them. And This kind of systems are powered by neural networks. Medical image analysis, astronomy. Very interesting application is, for example, if you have a flooded areas or disaster areas, is to rescue people. For example, you can picture with a helicopter the whole area, and then computer system will determine where exactly people are in that area and where to send actually help. And it saves hours in rescue operations. In a very, very cool application is self-driving vehicles. On this picture is a Google car that is using to kind of develop it. It's used to develop the technology, and that is the Google 2014 project. This car is running around Google campus, and it's powered by neural networks. Google is planning to produce the technology ready for public transport, for actually public roads by 2020. And this is very big topic now in California. Everyone is trying to work with self-driving vehicles. Tesla also has now this autopilot for all of its models already in production. And so capitals of and cities in Europe, they're trying to test and put in production self-driving buses, like Helsinki, Berlin, now Oslo. These projects are ongoing, so in a couple of years, we'll see those buses as public transportation systems. Speech recognition, automatic translation, chatbots, text analysis. In cancer research, we use neural networks to predict patterns in protein structure. We analyze features of genomic data to predict, for example, if that person with that cancer would be eligible for a certain cure from the cancer. We can use it in art. We can style our pictures with some...
That's her.
No, I just found it somewhere on the web, actually, with some famous artwork. So, and that is a fun application, but this also helps to popularize the technology. So that is the kind of problems that we couldn't solve at all if you wouldn't have deep learning today. So now, how did it start?
Yeah, I will tell some brief history of neural networks. Don't fall asleep. I think it's actually quite interesting. We need to make a thriller about it. So, neural networks have been subject of a great interest for many decades. In fact, the era of neural networks can date as far back as 1940, because already in 1943, when we were struggling in the Second World War, no, some of us at least, our parents, some countries, so McCulloch and Pitts created the first mathematical model of a neuron, and we will show you this model later. But for now, I just want you to keep in mind that neurons are the very building blocks of neural networks. And about 10 years later, training procedure was invented to actually learn these neural networks to do some stuff. And needless to say that expectations were huge. There was a lot of hype around neural networks, comparable probably to hype we have around networks now. And people start thinking that artificial intelligence is just around the corner. Of course, it was not. And then in 1969, a famous book was published by Minsky and Papert named Perceptrons. In this book, they described a simple neural network and analyzed it. And the result of this analysis was rather discouraging, because it showed up that such simple networks are unable to do any sophisticated tasks. For example, it cannot even classify data which is not linearly separable. So disappointment was enormous. Impact of the book was also very big, because it started an era which is known as artificial intelligence winter. It's kind of a neural network decadence, and during this period, neural networks were not considered like real science, and researchers in the field were considered like some strange guys doing some pseudoscience. Nobody wants to talk to them. Yeah, so dark time it truly was. Really, really dark time. Hard to believe now. Well, in 1989, one of the pioneers of artificial intelligence research field, Jan LeCun, quite a famous guy, he invented a new type of neural network which was able to recognize handwritten digits. And we will show you this later in quite a detail. So the bank check recognition system he helped to develop was widely deployed by National Cash Register and a set of other companies, and were scanning over 10% of all handwritten checks in the United States in the late 90s and beginning of 2000. And that could be a breakthrough. That could be the end of dark times and start of new era. But unfortunately for neural networks, fortunately for machine learning field, support vector machines as an algorithm was invented by about this time. And it showed about same performance as neural networks by that time, being considerably cheaper to train. And by considerably cheaper, I mean it required less examples, it was faster to train. So as a result, all the major interest, all the money, and all the researchers went to the field of support vector machines, leaving neural networks aside. Then
does anyone know what support vector machine is? And that is an algorithm.
Yeah,
of course you know.
It's
That's
just
an algorithm in machine learning, just view it like that. Another algorithm, not the neural network.
Yeah. Well, then Millennium came and brought us new hope. In 2002, a very famous person in neural network field, Jeff Hinton, invented a training procedure which allowed for the very first time to train networks which had hidden layers and more than one hidden layer. The idea of algorithm was quite interesting because he made neural networks to train by themselves to some degree, and then that just fine-tuned them in the end. At about the same time, GPU computation came along, and that allowed neural networks to start slowly rival support vector machines. Because with the right amount of data, neural networks having much better performance, or at least better performance, while support vector machines getting to the point of not being any better. So a couple of years later, Canadian Institute of Advanced Research, Canadian Institute for Advanced Research, also known as CIFAR, invited Hinton to lead a small group of scientists, providing small but sufficient money to keep the research moving. And I cannot stress enough the importance of this happening, because already 2 years later, Jeff Hinton and his team hatched a conspiracy to rebrand the very unpopular term of neural networks to something called deep learning. Because, as he mentioned in one of his interviews, if you mention neural network in any kind of title or description of your research or a paper, it will go directly to the trash bin. Nobody wants to even look at it. So they used known marketing trick, rebranding, and it totally worked in the field of science. We're all humans after all, no matter how clever we are. So they called it deep learning, and that's what we know now. Actually, we address the term deep quite often. What deep basically means, strictly means, means more than one hidden layer. So we all operate with deep networks now. So next happening and next breakthrough happened in 2012, when Jeff Hinton, again, and his team achieved outstanding performance in ImageNet competition. ImageNet is an annual competition where teams of researchers submit their work and they compete in recognizing objects and scenes on images. Did you know, by the way, that as for today, computers are already officially better than humans in these tasks? There is a supercomputer called Minghua at the Chinese company Baidu, and it documented better performance than a human being. So we're already behind in that as well. Well, back to history. Not so long time ago, at 2015, Elon Musk and others announced founding OpenAI organization. OpenAI is a non-profit, open organization with a main goal to develop artificial intelligence in a way which is safe and beneficial for humanity. And just 2 months ago, in November of 2016, giants like Microsoft, Facebook, Amazon, IBM, and one more, I don't remember, it's 5, they announced actually coming together, not competing, but coming together for what they call a partnership of AI. And Partnership of AI is an organization which study and develop artificial intelligence technologies and also advance public understanding of artificial intelligence in a way it influences society. I think it's quite cool. So what I want to say is we all here, we are lucky to live in a very time of something big happening. In fact, some scientists, most of scientists or some very popular scientists agree that by 2040, we will achieve technological singularity. And when I start thinking about it, it's just crazy. So as a result, as a wrap-up on the history part, because we're already by now today, I just want to say that neural network success, as we have it now, is a result of persistent work of few data scientists, supported by technological revolution, provided with enough computational power, and of course, very important, the vast amount of data, because all the files, all the information which is available on internet is very important for neural networks to succeed. So I hope it was interesting. Sounds for me like a thriller. Anyway, it's all cool, but I mean, we really want to know how it works. So you see, people build neural networks based on a human brain analogy. And human brain is built of about 10 billion cells called neurons. Neurons have an amazing capability of gathering, processing, and transmitting electrochemical signal. This is an artist's representation of how active human brain looks like. I can look at it indefinitely thinking, oh, that's happening here, but it's also happening here as well. This is kind of mesmerizing. It shows me what I'm looking at how it works. So, neuron. This is a picture of a neuron, kind of course. Neuron consists of 4 basic parts. It's a cell body called soma. It's dendrites, and those are small things at the top. Those are connection to other neurons. Then you have axon. Axon is a cable-like element. You can see it as a long one. And axon can be covered with a thin layer of myelin. The role of the myelin is to speed up a transmission of a signal, and you can think about it as an insulation of electrical wire. And then finally, there's a synapse. Synapse is a gate-like element which decides if the result of processing which came through axon should be sent on to our neurons or not, if maybe signal is not strong enough. So basic idea is very simple. Get a signal, process it, and send it or not to our neurons. And that would be abstract representation of a neuron. Get a signal from our neurons, process it, send it on. Each neuron can be connected to up to 10,000 other neurons. So that means that neurons are communicating to each other via over 100 trillion synaptic connections. And 100 trillion synaptic connections is equivalent of a computer with exaflop processor. This is inside here, inside each of your heads, running on almost zero electricity. That's amazing. So now we all know what the neurons are, and Katya will show you a mathematical model of it.
So I will show the model. It will be a little bit of mathematics, not much of it. So neural networks is a model that is inspired by what we think computer brain works. And it's actually what it is a set of nodes and set of connections between them, somewhat like graph, some are nodes and edges. But unlike graph, it's very structured. So it comes in layers. There is input layer, there's some hidden layer, one or more, and there's an output layer. And we are doing calculations between those layers. So our input layer is actually a data that we want to analyze. It could be image, it could be sound, it could be video, or it could be whatever data that we want to classify, for example. And in image recognition, that's an image. Output, it's a set of labels of what we know about our output and what we want to predict. For example, if we are doing image recognition, and if you are trying to identify if there is a cat or dog on a picture, that would be cat and dog. So how calculation is done within the neural network, if we look at the node of neural networks, that is a computational unit that is connected to the nodes of previous layer with some signals with the edges, and they are assigned some weights. And so we do the calculation of the node A1 in this case, based on the previous layer nodes and the weights of these connections. And then the calculated units is, the calculated value from that unit is propagated further on. And that's done with all the nodes in the neural network. That process is called forward propagation. So let's consider just one unit, what's happening in here. So A is our unit that we want to calculate, and we call it activation. So what we do, we apply some function that is based on the previous layers and weights. And we apply that function to the weighted sum of this previous layer nodes. In this case, it's input node, x1, x2, x3, x4. And then we have a weighted sum of it, and then we apply some function to it. So the function applied to it, it's called very often sigmoid function, for example. It could be other function, but I'll just chosen sigmoid for simplicity, I would say. And here is actually the graph what this sigmoid function does. What it does, it converts the numbers into the range between 0 and 1. So very large positive number, it converts to someone asymptotically equal to 1. Very large negative number, it converts someone asymptotically equal to 0. So that's what it does. And that is what is actually happening in the calculation unit in a neural network. That's quite simple so far. So if we look back on this graph, we see that there is some values, and then signals are being propagated further to the middle layer. For example, in this case, in red, I see that there are input layer nodes, x1, x2, x3, x4, and then we use it to calculate A1 unit and then calculate Y1, the output unit. And we do the same with A2 and A3, and that process is called forward propagation. So now I introduce one little concept that we'll just use in an example. So very often in neural networks, we use something called bias. So we add another node that is equal to 1, but it has a weight. And we just do it for network flexibility. So it's not very important to understand the model, and just because we use it in an example, I just introduce it here. So what I'm going to do now, I'm going to give you some examples that will give you intuition how it works. So now is the first example. Here is a very simple neural network. We have 2 input nodes, and then bias unit, 2 input units, bias unit, and output. So we have our sigmoid function that is applied to a weighted sum of our input units, which would be in this case this. We have weights minus 50, 30, and 30. And this minus 50, 30, and 30 we calculate that, and then we apply sigmoid to. And I'll remind you what sigmoid looks like. And then I can tell you that x1 and x2 is a binary input. Anyone has an idea what function it is?
Except for Evelina.
And Jennifer.
And Jane. Okay.
Anyone has an idea?
We will ask you one more. Yeah, please?
Yeah, it is. Yeah, I know that you knew. Yes, it is an n function. So let's calculate it. So first, if both x1 and x2 is equal to 0, then we get minus 50, and sigmoid of minus 50 would be 0. Then if 1 of x is 1, then we get minus 20, which is also 0 if we apply sigmoid to it. And here we have 0. 1 and 2, we have 0. If both x1 and x2 is equal to 1, then we get minus 50 plus 30 plus 30, that would be 10. And that would be asymptotically 1. So here we get end function. So we calculated logical end function using that simple neural net. So, and that is as simple as it is. Also, I will show you a little bit more complicated example. That is, would give you better intuition about neural network with the hidden layer. So I'll show you the function, logical function, XNOR, which is equal to 1 if both x1 and x2 is equal, and 0 otherwise. So that is nonlinear dependency. To calculate that, I would like to write it down as a combination of simpler functions. And I'll write it down like that. So x1, XNOR, x2 is a combination of x1 and x2, and then not x1 and not x2, and OR function. And let's build a neural net that would calculate it. First, we take a neural net that calculates our end part. We have just seen it. Then we take a neural net that calculates our not x1 and not x2 part. And I will not go into detailed calculation of that, but if we do that, you will see that this is actually calculating what we want. And then we combine these two to create a hidden layer. And then we apply that hidden layer, these values, to the next layer, where we calculate our output. So let's calculate it. If we have A1, this is our calculation unit, computational unit. So we have calculated end, as we have seen. Here is sigmoid, again, just to remind you how it looks. Then we calculate A2. And that is exactly what we see, the values that we see on this tree, not x1 and not x2. And then we use those A1 and A2 calculated values to calculate the final result. So we apply it to our third layer. And then we get the result that is XNOR function that we wanted. So we created a neural net that contains a hidden layer, and that can calculate that nonlinear dependency. And you can see that the neural net is actually propagating that knowledge from the input layer to the output layer. So it kind of learns a hidden layer in this very simple case. So that was the intuition about how it works. And Natalia will give you a tour into very exciting part of neural networks.
Yeah, I'm going to talk about neural networks types. And neural networks types are defined by topology, and that's the way neurons are connected to each other, inside layer and between the layers, and also activation function, of course. So what you see on this slide is a very simple neural network, infamous perceptron. It's very simple. One input layer, one output layer. It's feed-forward, and by that I mean that data is propagated from input to output, and it's fully connected. Fully connected means that all neurons on the first layer are connected to all neurons to the next layer. That's it. As you already learned by now, this network is not very powerful and cannot classify nonlinear data. Well, if we introduce a couple of hidden layers in between, we got so-called multi-layer perceptron. And those networks are much more powerful, and they can represent sophisticated dependencies in a data. This is, I think, the most used network in neural networks fields, because it's really easy to understand, easy to write, and it's quite powerful. The typical usages of multi-layer perceptron is regression, classification, sometimes dimensionality reduction. As you can see, the data flow is still feed-forward, but if we say we enable data to flow also backwards, we get so-called recurrent neural network. What is interesting about recurrent neural networks, it's not feed-forward anymore, it's bidirectional. Also, it's believed that having enough units and enough depth, such network can represent any kind of data dependency which traditional algorithm can. What is also interesting about recurrent networks, if you start thinking about each step as a layer, then each recurrent network becomes a deep network. But the depth occurs not between the layers, but between time steps. That's what I'm talking about. Let's say we have a data, and we send it in to first layer, hidden layer, then we send it to second hidden layer. And if network wouldn't be recurrent, by now, at third time step, we would be out and done. But since it's recurrent, the data is sent actually back again to second layer, and then to third layer, and then again and again. So each recurrent network is a deep network in itself. Recurrent networks are believed to perform very well in any kind of sequential analysis, and by this I mean speech recognition, video content analysis, and so on. Next network I want to address is very interesting, and it's also very simple. The type of network is autoencoder, and it's one input layer, one output layer, and one hidden layer in between. What is interesting about an autoencoder, that amount of output nodes is exactly equal to amount of input nodes. And if you ask, where's the catch? What is it doing? The aim of autoencoder is to learn representation of the data and then reconstruct it at the output. The typical usage of autoencoder is normally denoising and data compression. In the slide, I have a 4-dimensional input, then I compress it to 2 dimensions, and then I reproduce it again to 4 dimensions. And for example, if you have some kind of dust on a picture, when you compress and you recreate again, the dust would be gone because it's noise. And autoencoder is clever enough to figure out it's a noise and just remove it because it's not needed to reconstruct the data. It's not containing any significant information. While autoencoder in itself is quite simple. If you take several autoencoders and put them on top of each other, you have so-called deep belief network. And deep belief networks, want to have deep means something cool. Deep belief networks can perform very interesting tasks and very sophisticated tasks, like, for example, object recognitions. Speaking about object recognitions, we come into the main part of our presentation, and it's convolutional neural networks. Convolutional neural networks have been very successful in recognizing objects, and it's a type of network which was invented by Jan LeCun in 1989. So those networks are networks which are powering robotic visions. Those networks are recognizing traffic signs. Those networks are behind self-driving cars. But originally, they were inspired by a cat visual cortex. And let's speak about cats. we speak about cats all the time. So this is a picture of a cat, right? You can see a cat and a laptop. It's her cat.
Yeah,
Just saying. Okay, let's have another picture. And you see a cat and the paper and the floor. Pictures are different, but we immediately see a cat on both of them. What convolutional network does, it can identify the feature of an object, in our case, cats, and find them on an image, no matter where an image with features are. So if I look at these two pictures and I think, what are features of a cat? I would say it's eyes, nose, mouth, whiskers. I'm a human. I know what to look for. Convolutional net doesn't know what to look for. But having enough examples, it can actually learn what to look for. And we call it extract the features. What it actually does, it compares all the training examples of the pictures you give it, and by having about same image patch at about same location, it figures out that's probably a feature. So we can use it to recognize those objects later in time. Each convolutional network contains of 4 basic layers. And those layers are convolution, nonlinearity, pooling, and classification. And we will walk through each of them in a very detailed manner. So we will not look at the cats, because cats are very complicated creatures, and everybody who ever had a cat knows they are too complicated to deal with. So we take a classical example here, very classical, closer to us geeks, numbers. This is a classical example in the machine learning field, recognizing a handwritten digit. There is an existing data set publicly available containing this handwritten digits. So let's take an image of 8 and try to see if we can tell it's an 8 or not. I would say that a distinct feature of any 8 I can imagine myself would be a crossing capture in the middle. That's our feature. So now we have a feature, and convolutional net will walk through the image and try to find this feature in any possible place. The search is done with very simple math. We assign all pixels a number. We assign -1 to light pixels and 1 to dark pixels. Do the same with the feature. And then to see if feature matches or not, we multiply corresponding numbers on pixels and the image patch. And that is an example of a full match. We multiply -1 with -1 plus 1 multiplied to 1, so we have 9 ones. We summarize it, and then divide by number of pixels. So the full feature match, ideal feature match, will give us 1. And that is an example of not so good feature match. It gives us -0.11. Trusty mathematics is right here. I checked it like 1,000 times. So we know the mathematics behind the convolution. Let's do convolution. We start from a top left corner, and we slide an imaginary window along the image until we cover it all. What we get is an array. And that array shows us where on the image our feature matches best. For intuitional understanding, we color-code it, with the white being 1 and the best match, and the -1 being darkest and the worst match. So this is a feature map. By now you probably wonder, okay, this is all cool. How do we map it together to the nodes and layers and connections we just talked through? Let me show you that. We already agree that all pixels have a number, so we can represent our input image as an input array, in our case 8 by 8, 64. And same with the output result. It's also an array. And we call it an input nodes and output nodes, both inputs and outputs. What we also know that this output node is the result of calculation of these 9 input nodes with some feature values. In terms of neural networks, that means that those 9 input nodes are connected to this 1 output nodes, and the feature pixels are actually weights on connections. Activation function is average. Isn't it cool how they apply mathematics to kind of the convolution process? I find it fascinating, honestly. But anyway, okay, never mind. This was an example of one feature. Of course, usually it's more than one. So we repeat convolutional process for every feature. And what we end up with is a set of images which we call feature maps. And of course, amount of feature maps is same as amount of features. As you probably understand, a number of mathematical operations is increasing really fast, with number of pixels on a picture, number of pixels on the feature, and pixels on the image on a feature, and of course number of features. So what I want you to keep in mind, convolution is very computationally expensive operation. That's why we probably need GPU for that. Okay, next layer is called pooling. And what pooling does, it actually shrinks our image to something much smaller while preserving the most important information. The most important information for us is where is the best feature match. For pooling, we usually choose a window like 2 by 2 pixels, sometimes 3 by 3. And inside the window, we take the maximum value, which is the best feature match. We don't care where exactly on the image this feature match is, as long as it's inside the window. So let's do pooling. We slide the imaginary window, and we do our pooling process. That's it. By the end of pooling process, our image shrink by about 1/4. Next step, and that is how you do it in layers and nodes. One node, output node, is connected to 4 input nodes. Activation function is maximum, and the weights are 1, because we don't manipulate with any values inside the input nodes. We just choose the maximum as is. So that is pooling. Next layer is rectified linear. Behind a very scary name, I don't know who invented these names, really. But the mathematics is really simple. Take all negatives, replace with 0. That's it. That's what it's behind. Just replace all negative values with a 0. The role of pooling of rectified linear unit is actually to improve mathematical performance. That's it. So what we've done so far? We've done convolution to find where the feature is. We've done pooling to shrink the image, or feature maps in our case. And we've done rectified linear. Trust me, we're almost done by now. This is a nodes representation of the same process. Last layer. Last layer is called fully connected. That's also the layer which takes a decision to which class our image belongs to. To do the decision, we take all the results so far we have from the convolution pooling and rectified linear and join them into one huge input array. Each value of this array have a vote to cast to decide if an image is 1 class or second class. In our case, first class, yeah, it's an image in 8, and our no, it's not an 8. So some values can have a stronger opinions about which class our image belongs to, and those get more important votes. Or in case of neural networks, they have bigger weights. And that's actually how convolutional network works. We are through the process. It's convolution, pooling, rectified linear, and fully connected at the end. There is, of course, a catch. When I started a presentation of convolutional net, I said, here is a feature, and when the fully connected layer came to take decision, I say, oh, those values are more important. Of course, we do not set these values by hands. Convolutional net learns it during the training process. So for training process, we need a training set. And we know in advance what the result for this training set is. So initially, we identify all the things we need for network with some initial weights, some randomized weights. And then they send the image in, and they observe the result, and we correct our network to get closer to the expected result. Let's say we send an image of 8, and we got a result, it's not an 8. So we know that result should be, and we know what result is, which we get with the network as it is. So we know the error. We know the error, and we know the mathematics behind the last layer, which is fully connected in this case. So we can calculate the error of the last layer, the error of the current settings of the last layer. Now we know the error of the last layer, and we know mathematics of the next last layer. So we can calculate an error of the next last layer. And so on, we can calculate all errors of all layers. Then we know all errors, and we know the expected result. We can tweak our network and adjust the values to get slightly closer to the expected result. And then we send next image in and observe the result. And this is repeated for all images in our training set, and sometimes not even once. The process is called backpropagation. And it's slightly complicated math behind it, so I'm not going to walk you through that. I just want to give you some intuitional understanding. So that was a simple convolutional net with 4 layers. Actually, I think you agree with me, not a rocket science, right? Just a net.
It is a little bit of rocket science.
Okay, but it's not that rocket science. That was a simple network. Of course, each network can have more than one of each type of layer, and it will form a deep convolutional network. What is interesting about deep convolutional network, as you know how it works now, you can imagine that as deeper we go in a calculational process, then features we get are getting kind of proportionally bigger in comparison to initial feature. And it's also becoming more complicated. In the features deep inside the convolutional network, you can actually see patterns. And probably difficult to understand, but that's what I mean. This is a convolutional network trained on faces. And this is the first layer, and you can see some indistinct spots and edges and I don't know what. But the last layers are clearly looking like human faces. And I think this is cool. Sorry for that.
I think that's very cool because I mean when I started to learn about neural networks, its architectures and types, and I bumped into some videos and just I wanted to experiment with that, and I said, oh, okay, let's create a convolutional network, and I'll explain what is convolutional network. Oh, everyone knows what convolutional network is, and I was like feeling not so good about that because I didn't know what it is, and I think now you can be of those everyone who knows what convolutional network is.
Yep.
And that would be, I think, that is a very cool explanation, I personally think that.
So I hope you all understand how it works now. And now the probably the most exciting part of our demo, of our presentation, we promised you a demo. So demo time it is.
So before we showed the demo in two frameworks. And before that, what I wanted to stress about is that like 10 years ago, maybe 5 years ago, maybe even before, maybe even 3 years ago, even 3 years ago?
No, 5.
Okay. So then deep learning and neural networks and working with that was the privilege of departments of research institutions or big companies who could experiment with that, who could write the code from scratch in C++ and do their experimentation and try to train the networks, and those who had access to data and access to very fast computers who could actually train the network. And today there are lots of frameworks, and those are open source, and those are implemented all the sigmoid functions and all the architectures, and then it takes really few lines of code to implement your own network. And that is for everyone, for hobbyists, for hackers, for researchers, for programmers, for everyone who would like to experiment with that, who build their own app, AI-powered, or just want to learn what it is. So that is kind of a very good time to start playing with that, and it doesn't require a lot of investment in training and learning.
But of course, everybody who is doing with data science knows that the trick is not to write a network. The trick is always to collect the data.
And that's true. That's actually very true now. So we'll give an example based on MNIST case study. Anyone heard about MNIST before? Yeah.
Yeah, of course, I just told about it like half an hour ago. Come on, guys. Are you all asleep?
So MNIST is a database of images that represent a handwritten digit. And our goal is to create a neural network to predict correct digits from 0 to 9 from the image of that digit. So we see that the image of the handwritten digit, and we want to see what we want the system and the network to tell us what digit it is. And that is a kind of example of what this digit would look like. For example, this is 8, and then the whole bunch of 8s, a whole bunch of 9s, because people have different handwriting and they write it differently. And what we do, we have images that is 28 by 28 pixels, and it looks like that. And then it's just the grayscale intensity of the pixel, that we see in the array. And what we do actually, we take each pixel and we reshape it into big array. So we don't use it as a matrix, we use it as an array. And that's become our input layer. So it's kind of 0 pixel, pixel 1, pixel 2, and then we come to the end. And then we have, for each image, a label that is correct. For example, if there is 9, then we have a label 9. For all the 9s, for all the images with 9s, we have a label 9. So we use that data set to train the network, and this is exactly architecture that I will use in my demo. So this is a simple perceptron, and then it has activation that's called softmax, but it's not that important at this point. So I'm doing demo now?
Yep, we're doing demo now.
But then we need to switch.
Yep, I need to switch, but your computer is asleep.
Okay.
So Katya is using TensorFlow with Keras on Python. And she's doing perceptron not because of TensorFlow cannot implement something more sophisticated. Of course it can. just because it's more fun to show slightly different stuff.
That's right. So what I do here, this is Python API. And what I do here, I just load my MNIST data, and I wrote my train set and test set. I do it, so I used my train set to train my network, and I used completely different images that my network haven't seen before just to test it. And what I'm doing some reshaping. And actually, this is my network. This is like exactly 3 lines of code to design it, and then compile, and then I fit it. So it's 3 lines of code, exactly. And then what I do, I fit. I call fit. So I actually train my network by using the MNIST images, and then I save it into the file. So I'll just run it now. It just runs maybe 15 seconds. It's using TensorFlow backend. And TensorFlow has also its own API that I will not show in that presentation. So there's lots of options.
Of course, everybody in the audience is very familiar with Python, so you obviously understand everything which is on a slide, right? That was a joke.
It's not a joke at all.
Oh, okay.
So we trained our network, and we saved it on disk. And what I will do now in my demo.
Accuracy is 92%. And I must say it's here. 92%. Okay, almost 93, but still, for object recognition by nowadays, it's pathetic. That's
pretty bad. But it's very good for the presentation. In real life, it's pretty bad. But, yeah. This is very simple.
Just for example.
This is very simple architecture of the network. So what I do here, I load my model. So I saved my model in JSON file and H5 binary file. I load my model in here. And then what I do, I just select the random image from my test set. And then I kind of visualize that label and visualize what data was predicted. Don't that look something like that?
Yay, that's lifetime digit recognition on a Python using TensorFlow and Keras.
But we are not done yet. No. We have a real convolutional neural net.
Yeah, well,
another framework.
I'm not so good in user interface. Yeah, I'm switching back. Okay. I do my part of the demo with Microsoft Cognitive Toolkit for deep learning. And recently, it was renamed to Microsoft Cognitive Toolkit. Before, it was Microsoft Convolutional Network Toolkit. And Microsoft rebrand their stuff more often than I'm able to remember. So I just still address it as CNTK. Sorry for that, Microsoft. So everything you need to know about CNTK is available at cntk.ie. Type it in your web browser, and there you have it. You have all the tutorials, all the explanations, all the basic part, how to install it step by step, very easy. And the most important, there is a link to GitHub where it has all the code, so you actually can see how it's written. And you can participate if you feel brave enough. I don't. Yeah, okay, so it's open source, obviously. And it's cross-platform, runs on Linux, Windows, Docker, you name it. It's production ready, it's already used in production. And it scales to multiple GPU, it scales to multiple servers, and it scales to GPU in Azure. This feature was implemented just like maybe 3 months ago. So it's quite cool. Why I like CNTK is because it allows me, and you, of course, everybody, to compose almost any kind of networks with very simple building blocks. And those building blocks are coming predefined, if you want to use something predefined, but it's also flexible enough. If you need something special, you can write your own building blocks. And of course, some simple models are already included, and you just don't need to write anything. Just like, I want this typical network. And there's so many inputs, so many outputs, so this is how I want to train it, and you're ready to go. Basically, it takes some few lines of code. And then you have a script. So it's actually, originally it was only script language called brain script. Okay? And you define your network with a script. You define what you want to do. Usually it's train and test. And you run your script, and it spits out a model. I mean, it trains the model. Yeah. So it's training. Then you can, when you have a trained model, you can evaluate it. That means you send a question in. And you say, OK, what neural network, what do you think? And it gives you an answer. And then, of course, if you are satisfied, you deploy it, and you're ready to go. So you can define network, as I said, on brain script. But recently, they published update. In the latest version, you can also use Python for that. To evaluate the model, not to train, but to use already existing model, you can use from C++, C#, Python, you name it, a lot of bunch of languages. My demo is done on C#, because I used to be a C# developer. So I will show you. First, I just want to show you my data. Here it is, labels, and all the features, all the 84. Katya already explained it, so I'm not stopping on it. That's my script. I say there's a command. The command is train network, test network. I need to test so I know how good my network is. And of course, we have different data sets, one for training, one for testing. Then there's a data dir, blah, blah, blah. So it says where actually I find the data. The most interesting part is here. That's where I define my network. And that's actually the network definition. All the known stuff. Convolution, max pooling, again convolution, again max pooling. Here is rectified linear, and dense layer is actually a fully connected one. So that is description of a deep convolutional network. It's like literally 10 lines of code.
10 lines of code.
9, actually. It's even less. So to run my network, all I need to type is...
To train, you mean? Or?
Yeah, to train my network. I need CNTK, and then I specify config file. Of course, you need to install CNTK on your machine as a framework, but that's not complicated at all. I have it installed, so I will not go through it. So, and then I specify my config file, and then I run it. In my case, I already ran it before, so my network is trained, so it will skip the training process because it understands I already have a model, so it will just validate it. So it has completed, test. What I'm interested here is this. I didn't train it long enough, or it's not very complicated network, so it gives me about 0.9% error. Not so good, but good enough for demo. So my network is actually stored as a file. It's that one. It's 395 kilobytes. So now I will build a C# application, or I have it built, I will show you, which loads these networks and call it with a CNTK framework. That's my web application, standard. It's also from demo. I didn't build anything from scratch. I just took a tutorial. It's like straightforward. This is where I build my network. I load it from the file. You don't really need to understand. The only thing I changed in an example, I just provided my file where the model is. And here, I get my BMP file, which I upload, and just make a feature by making an array out of pixels. And that's the place where I evaluate my model and get the result. So literally, it's one screen code. Now let's run it and see if it works, because today in the morning, suddenly it's like, oh no, access denied. I don't know why, typically. So I run my super web application. See, I'm very good on user interface, apparently. Vanilla JavaScript, no crap. Let's send in picture and upload and check. First time it's a bit slow, it's loading. Well, hey, CNN thinks it's a 1. Let's take another one so you don't think it's a hard-coded stuff. Hey, upload and check. And CNN thinks it's an 8. And that's basically how simple it is to create your own deep network and to run it and train and then call it from your code. It's very simple. So that was our demo. Thank you.
And that was it for the talk, actually.
Yeah. We have a meetup in Oslo. It's about 850 members by now. And we run different topics. Deep learning included, usually more like general machine learnings. We do it once a month, but sometimes more often if you have more to talk about, because it's a side of a work, so it's free time activity. So if you ever run in Oslo, check. Maybe this day we run some exciting meetup. If you want to talk, contact me at Illumico. That's me, because I'm an organizer, so we can make a meetup for you. Yeah, and the second tweet is Katya Geek. Mm-hmm. And what we want you to bring from this session is that neural networks is very simple. It's like the bar now is very low. Go home, read about it, try, build some evil or not evil artificial intelligence and get us into a bright future. Thank you very much.
Thank you.
We forgot to ask about questions, but we are still here. Just come and ask.
Yeah, I think we run out of time. I think we still have some.
No, we still have some time. But yeah.